For this lesson, we're going to be looking at the normal approximation to the binomial distribution, and we dealt with the binomial distribution in Chapter 5, I believe. And then in Chapter 6, we've been talking a lot about the normal distribution. Sometimes it's appropriate to use the normal distribution for a binomial distribution. And first of all, we'll just start with when this can happen. When you have your probabilities for your binomial distribution, P and Q, P, I think I've got this on another slide, but P is that probability of success. First of all, you have to check if N times P is greater than or equal to 5 and N times Q is greater than or equal to 5, and they have to both be satisfied, all right? So that's critical. That's one of the very first things we'll look at. And then if that happens, you can use the probabilities from a normal distribution, and you're going to be pretty close. It's actually not exact, so the binomial distribution is better, but before we had calculators and technology that would calculate so many things for us, there were lots of charts and information that was easy to get about the normal distribution, and so being able to use that approximation was much faster. With the advent of all the technology we have now, it's not quite as useful to us, but yet it's still hanging on. It's kind of like we're in there in between where you haven't given up the approximations yet. These formulas that are down here at the bottom of the slide are not new. You do need them, but they're the same ones we used in Chapter 5 when we did the binomial operation. You can find the mean with N times P and the standard deviation by the square root of N times P times Q. One thing that is different about the binomial and the normal is the binomial approximation is discrete. That means we had whole numbers, like the probability of getting 1 or 2 or 3 or 4. But the normal approximation is continuous. It can use, 1.4, 1.5. And so one thing that makes the approximation from the normal a better approximation to the binomial is to compensate, and that compensation is called a continuity correction. So every single time you're going to use a normal approximation for the binomial, you need to do a continuity correction. That continuity correction is an adjustment of 0.5, which gives us that halfway in between our two discrete values. So sometimes we subtract 0.5 and sometimes we add 0.5, and there's another slide coming that'll show a little bit more detail about that. But you have to make an adjustment of 0.5 for the continuous nature. So before I go on, just remember, and I mentioned this, but here's those letters that we used in the binomial distribution. N is the number of trials. X, and that's the one we're going to do the continuity correction on. X is the specific number of successes. And then the probability of success is P, and the probability of failure is N. And since total probability is equal to 1, you can rearrange this little equation over here. P plus Q has to equal 1. 1 minus P is Q, and 1 minus Q is P. There's a lot of rearrangements of that. And success, of course, doesn't have to be a good thing. It is just getting whatever you were looking for. So here's kind of the visual that you need to get. When we did our binomial distribution, it was like a histogram that had some sort of a normal shape. It was low on each side and higher in the middle and pretty well symmetrical. That's our binomial distribution. But when we put this continuous curve on it, that's the normal. And so you can see that sometimes our normal approximation is going to be a little bit lower than our value, and sometimes it's going to be a little bit higher, and that just kind of depends. The more values we have going across the bottom, the more you can see where it starts to look smoother. So the one here on the right in green is a smoother, it's not smooth, but it is a smoother binomial distribution than the one that's in blue. So anytime we have sample proportions and we do a distribution of that, then the distribution of the sample proportions tends toward normal. It's not exactly the same. Again, the binomial is discrete using whole numbers, and the normal is continuous, and we'll have to do a continuity correction. So whenever we work problems using this approximation first of all, check that n times p is greater than or equal to 5 and n times q is greater than or equal to 5. If either one of those is wrong, if n times p or n times q is less than 5, then you cannot use the approximation. It's not going to be close enough. If you can move on, though, the mu, the mean, is equal to n times p. You'll need to find the standard deviation sigma by doing the square root of n times p times q. Once you have that mu and sigma, those are what you're going to put into your calculator for the normal distribution. Instead of the 0 and 1, we will actually use those values to put them in there. Now, another thing we have to do is convert that whole number x by our continuity correction. And we have to figure out, what our boundaries are going to be. And they're definitely going to be bounded by either x minus 0.5 or x plus 0.5 or maybe both of them. So basically, we want to sketch on this last step. It says graph, but we're going to sketch that distribution and determine what our values are so that we can go into our calculator and we will use our normal distribution to solve problems. So really, the key section here is, can we use the normal approximation? And then if we can, find out what the mu and sigma are based on these little formulas, then we'll use our normal CDF in our calculator. So here's an example. Mendel has a famous hybridization experiment involving peas, and he expected that out of 580 offsprings of peas, 105 of them would be yellow. That would have been 25%. But he actually got, out of that 580, he got 152. So if we assume that his 25% is correct, what is the probability of getting 152 or more by random chance? And so again, we've got this little summary here. That means n is 580, the number of trials. The probability of success is 0.25 or 25%. We want to find the probability of at least 152 yellow peas. Now remember, that's because they're asking us, is this significantly high? It's never the individual probability, like the probability of 152 you're interested in. It's the probability of that many or more, or maybe that many or fewer if they're asking you about significantly low. When we interpret this, which will happen on the next slide, we're going to remember that how do we tell if it's significant? While 5% is not the hard percentage to use, what you're looking at is, isn't it less than 5% likely to happen this way by chance? If we're looking at lower numbers, that's going to be significantly low, and upper numbers significantly high. So if we want to work this problem, first of all, we need to check NP and NQ to see if we can use this approximation. NP will be 580 times 0.25. Maybe I should use parentheses because my decimals and times look just the same. So NP is 580 times 0.25, and that is 145. Okay, so that one is certainly bigger than 5. We know it's going to work. And you may intuitively just know sometimes, but for the purpose of this, I definitely want to crank it out. You'll also want to check NQ. So that's still going to be 580, but Q is 1 minus P, so that's going to be 0.75. 580 times 0.75 is 435. So those are both bigger than 5, which means it is fine for me to use this. So if we have checked it and decided we can use this, then you want to find the mean and the standard deviation. Well, the mean is n times p, which I've actually already calculated in just that little check, so I know that's 145. But the standard deviation that I need to use will be the square root of NPQ. So I need the square root of 580 times 0.25 times 0.75. So just punching that into the calculator the square root of 580 times 0.25 times 0.75, and I get 10.4283. Weird little extra symbol there, but I doubt I can erase that well. I did, what do you know? All right, so now we're going to take this information. We'll have this on the next page because I haven't finished here. There just wasn't enough room to get it all on one slide, but we found out we can use the normal approximation, and then I have calculated what the mu and the standard deviation is that I need to use. So the same problem here. What we've got here is the calculator display. Now what you can see on here is that my mu and my standard deviation are exactly what we just found on the previous page. Okay, so where did the other stuff come from? Well, don't forget you have to do a continuity correction. So to do your continuity correction, you want to think about your normal curve, and we're getting at least 152, which would mean I need 152 or more. But if you think about just when we're in the discrete listing and we're just counting the p's, we would be at, 1, 2, 3, blah, 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 and it keeps going, and eventually we get to 151, 152, and 153, and then that's just going to keep going all the way up until we get to 580. My concept here is to think about, first of all, in the discrete, what is it you want? You want 152 or more. 152 or more means that you want all of these. Okay, if you want all of these, then when you're looking at kind of drawing the line for your continuous, you need to draw the line right here. And what is between 151 and 152? That's going to be 151.5. So that 151.5 is why it says that my lower value down here is 151.5. That's just like saying, then when I went to this continuous value, the value right here where that line was needed to be 151.5. Now sometimes you're going to move up 0.5 and sometimes down 0.5. So you just have to consider, when you move, will you still include the value that you want? So if I had moved up, if I used 152.5, it would not have included the 152. But I need that included, so I had to move down. So that lets you know why I did the continuity correction of 151.5. I previously calculated the mean and sigma. Then this is underneath your normal CDF, just like we've used before. And you get a value over here that's 0.2665. What that means, really, that's pretty close to about 26%. Or really, if I were rounding, it's pretty close to 27%. It's not really that much yet, 26.65. But that's where we're going to say, based on significance, it's printed on here, but you can't see it anymore. Maybe I can move to select and move that. Significance is less than 5% probability of happening by chance, okay? So here we had the chances of this happening, getting 152 or more, was 27%. So that could easily occur, okay? That could easily occur. That is not less than 5%, so that is not significantly high. Don't forget, I said that this is an approximation. You could do this exact same problem with the binomial CDF like we did in Chapter 5. On the binomial CDF, you don't make a continuity correction. The concept of what you want is the same, but on the binomial is we do that count up 1, 2, 3, and eventually we get to 151, 152, 153. I always kind of go on both sides of the numbers I'm dealing with, and it's going to go all the way up to 580. But we don't need a continuity correction here. So if I need 152 or more, the part I'm highlighting is the same. I still want this part. However, on your binomial, it always calculates it from the left. And so on the binomial, what's going to happen is I'm going to have to put in 151, and it's going to add all of those values up for me, the probability of 1, the probability of 2, all the way up through the probability of 151. And then you can see I had to do 1 minus that so that I could get the other part of it. Okay? And that's because when we're doing our binomial, it's always going to go from the left. I don't know when they'll update the calculators for this program on that, but right now they still all go from the left. So we would get approximately a 26%, 0.49. So you're still going to have the same conclusion, but the probability from this binomial is actually more accurate. When we used our normal, so this one was the approximation, we got 0.2665, which was about 27%. When we use the exact binomial, we got 0.2649, which is closer to 26%. They gave us the same conclusion, but that 26% is more accurate. Okay? So what I'm really saying here is don't use the normal approximation unless you're instructed to do so. Now, you will be instructed to do so plenty in this particular section. But overall, when you're putting this all together, you've got to remember, if it's binomial, you should use the binomial unless you are told to use the approximation. That's particularly important to you on your homework, since that homework asks you to put things into like 4 decimal places, and you can see the binomial CDF versus the normal CDF has a change in that 3rd and 4th decimal place. So just make sure you recognize which one's more accurate and which one you should do. Now, I said that there'd be a slide about continuity correction. And again, this just has to do, should you go to the right or should you go to the left? And I think that this would just be an example. You may not have 152. Well, of course, you won't have 152 in all of your examples. But if you make a note or take a screenshot of this particular slide, I think it will help you know if you should go to the right or go to the left of it here, or which ones it includes. So, final thoughts then. When you are doing this, you need to check your procedure. Make sure n times p is greater than or equal to 5, n times q is greater than or equal to 5. If that works, you can use the approximation. To use the normal CDF, you have to have a mu and a sigma, so you'll need to calculate that with these little formulas. Then you need to make a continuity correction. Once you've figured out that continuity correction and you have mu and sigma, then you can just put it into your calculator under your normal CDF, and you'll be able to calculate that. Also, when it asks you significantly high or significantly low, you're trying to determine it really based on, is by chance smaller than 5%. And we've talked about that in some previous lessons too. So I don't want to drag this out. Do your homework. Let me know if you have a question. I'm happy to help.